So, thank you for the nice words. I'm happy to start this session. It's also good to meet so many old friends, fellow combatants, adversaries, yeah? But all good friends anyway. I think we owe something to the inspiring personalities of Walter Cohn and Bob Parr, that the atmosphere in the DFT community has always been, I would say, extremely friendly. I enjoyed that. It stands a little bit apart from other, say, gremia that I will also mention here. Okay, now let's see. Why doesn't it move on? I have only one button that tells me, yeah, okay. I think the path of DFT in chemistry has been rather different from physics, actually. I started around 1970, and then Slater's X-alpha method was in chemistry, or theoretical chemistry, I say the talk of the town. This was due to the multiple scattering method that Slater advocated and Keith Johnson actually carried out. And they made big claims. It was orders of magnitude faster than any of the existing ab initio methods. And they made also silly claims like the orbitals that came out with were better orbitals than the ab initio ones. It's a bit odd, but there was very little about Hohenberg-Kohn and Kohn-Sham. And if people mentioned it, there was an existence theorem, but it was not really serious because there was no way to tell how you would get this functional that they proved must exist. Right? Should I point somewhere or?
No, just let's check it.
It does not move.
It moved. It moved now.
Yeah, not very fast. The first meeting I ever went to was a meeting of the German theoretical chemists, but there was German spoken actually, but I was allowed there, and now let me try again. Well, should I point a longer time, or what should I do? Yeah. Here you can see the program. It was all about X-alpha scattered wave calculations, right? I talked about the method I will mention in a moment. So this was the program, a special session on the X-alpha method. And then in the evening there would be a forum discussion where Ulrich would appear. And I'm sorry, it is going to take time.
Let's check it, John.
Yeah.
I have to try it. Yeah, it's just
I do something wrong?
Try it again. Just one push. I think a little bit. Did it work? No?
No? So if you do it, it's okay?
Yeah. Just very soft. One time. Soft. Yeah.
There you go. Softer.
Okay. Okay. Good. Ulrich gave his talk the title X-alpha, na und. Even if you don't speak German, I think you get the gist of what his talk was all about. People hated X-alpha for some reason. They said, yeah, but the claims by Slater and Johnson were too bad. But I think there was something deeper. I think in the ab initio community, people had just left the semi-empirical methods. And they were proud of doing things precisely. All the integrals should be calculated, no approximations made, and then you would get the final right answer. And now we started with methods like the scattered wave, but also the method I will mention, that actually were more approximate. Okay, let me go through this quickly. We proposed at that time a basis set method. This is because the scattered wave method, with its muffin thinning of the potential, was actually awful for chemistry. You could not do geometries or whatever. But there was one problem. At the time, everybody would talk about the n to the 4th catastrophe of the ab initio method. You needed to calculate n to the 4th integrals accurately. And then I remember my fellow graduate student at the time, he tried to do a calculation on a very simple transition metal complex, nickel tetracarbonyl. He had to hire the supercomputer, we would say, the mainframe, over the whole weekend. And I remember we visited him, he was hanging up, I think 6 magnetic tapes with all the integrals, and you had to mount and dismount them on every cycle. So it was terrible. And then on Monday morning, he forgot to hang up one of those tapes, and the whole calculation crashed. So we were very convinced that we should try to do away with all those electron repulsion integrals. That was necessary. I come from an inorganic theoretical group. We wanted to do transition metal complexes and beyond, and so then you could not handle this n to the 4th integrals. And then the overriding consideration was that we should balance the approximations. If you have a limited accuracy anyway, because you cannot do a complete basis set or even a high basis set, so why calculate all those n to the 4th integrals to say 13 or digits, and then combine them to get a precise Fock matrix, and then your energies and orbital energies are not so good anyway. So we said, okay, maybe we can solve the problem by doing a 3D numerical integration of the Fock matrix elements directly. So that's up there, and we calculate all those matrix elements by a 3D numerical integration, and then actually you are free. You can use numerical atomic orbitals as basis functions or STOs. And then the step that actually allowed us to do away with the electron repulsion integrals was the density fitting. So if you do a least squares fitting of the density with some set of basis functions, and again we used Slater type orbitals, and we broke down the total density in maybe I should point that right, yeah, in diatomic parts, and then the fitting problem becomes very easy. You have n to the squared, the number of nuclei squared, but all the fitting problems are small because we use fitting functions on the 2 nuclei A and B. So then you have an order n to the squared. Let me see, yeah. So the fitting is n to the squared. I'm going too fast now. Yeah. So you would have an n to the squares problem, and if you have distance cutoff, if you have nuclei very far apart, it becomes an order n scheme. Okay, yeah, so you solve a couple of linear equations, that's not so difficult. The story is that subsequently, Samby and Felton in 1975 said, okay, we can do just the same trick in an ab initio code. And we have all the integrals over the Gaussians available. They also did the density fitting because that is then for efficiency very important. And they fitted also rho to the 1/3. And so they needed also numerical integration for that part. But then it's not so hard on the precision of the numerical integration. And the next step was taken by Dunlap and co-workers in 1979, where they did a density fitting scheme with an R to the 1/2 factor included, which is now actually done a lot. In the 70s and 80s, I will talk a little bit about the whole atmosphere at that time. Then people would say, yeah, of course, these DFT methods are n to the 4/3 scaling. But that actually was not a correct statement. If you don't do the density fitting, it is actually still n to the 4 scaling. If you use all the integrals. But this trick of doing the density fitting has actually very little to do with DFT, of course. It was more like a technical issue. And then in the 70s and 80s, there's a whole series of programs. I think Daniel Steller will talk about the MON code probably. There was D-Gauss, Paragauss, whatever. The LMTO method that Bob Jones will talk about probably is still different. The main application area was transition metal chemistry, catalysis, organometallic chemistry, for a reason. I will mention this. Why were people so angry about this method? So now we got to get to the debate. In my recollection, there was not much of a debate. Actually, people would yell at you at conferences. It was hated, right? I remember at one occasion, a few graduate students took me out to dinner after the meeting because they were so embarrassed with the behavior of their supervisors. And I really didn't quite understand what the problem was. But what would people say? Ah, the method is approximate. All this density fitting, terrible. Numerical integration, that's a bit odd because today we see an enormous surge in density fitting in all, so like MP2 is now done as density. This is mostly actually with Witten's approach of doing density fitting of all the products of basis functions. And then people realize that actually you can break down the n to the fourth problem into an n squared problem. This is called now tensor contraction or hypercontraction by people like Sherrill, Martinez, and Fermi. Actually, there are problems. The Oslo group did quite ingenious work pointing out there may arise actually variational instabilities if you do the density fitting on basis function pairs. So I cannot go into this, but so it's a quite active field of research now, and there's no people have no bad feelings about it anymore. Then people would say, yeah, this is all ill-founded. X alpha is terrible, and then DFT, and that's maybe there is some point. People didn't understand. They would say all the time, yeah, but you have only one determinant, so you cannot have correlation. And that is, as you all know, a really misunderstanding. Another point, which I think I'll talk about, is yeah, how can you use electron gas ideas for molecules? And still, that is a problem. There's no systematic way forward. We don't have a way to build better functionals. We have to use our ingenuity to do this. And a point that I was not aware of is that actually there was pretty little interest from the wider theoretical chemistry community, because the focus was totally on organic chemistry. WATOC is by far the largest, and the World Association at that time of theoretical organic chemists is by far still the largest quantum chemical organization there is. And of course, because the ab initio methods could not really do large systems, even transition metal complexes were difficult, people focused naturally on small organic molecules and tried to improve methods. I would say the X alpha, it was also called Hartree-Fock later at that time, and LDA codes, they were truly efficient enough and accurate enough to do lots of applications. And that is where we honestly focused on. There was a lot of chemistry that could be done, clusters, catalysis. Tom Ziegler has done a lot of work in catalysis. Relativistic effects were also a very nice field because you take uranium, you already have in the order of 100 electrons, so that was out of reach for the ab initio methods, and we could handle those. And relativistic effects are nice because you make only relatively small changes, and X alpha particularly was very good at changes. There was no interest or little interest from theoretical chemistry, quantum chemistry community. There was actually real interest from chemistry and industry. I mean, for myself speaking, we survived in that time with grants from major industries in the Netherlands, which was unusual. I don't think there was any other theoretical chemistry group that got those grants. But we did not get grants from the theoretical chemistry community. So, making things a bit more general, I think the main thrust, still maybe in ab initio chemistry, is well, we know that full GI in a complete basis is the solution. So we work at methods to get close to that, so that is like quoting John Purdue, the heaven of theoretical chemistry. And naturally there has been a lot of interest in properties. So a couple perturbed Hartree-Fock, all kinds of derivatives for properties and for geometry optimization. DFT has a different outlook. I would more like the first, almost like a mathematical approach, and then DFT is to me more a physics approach. There's the physics of correlation, that is the important thing. How does the exchange correlation hole look like, and how could we model that? Okay, this is the square hole that Slater proposed. You make a hole at the depth of the density at a particular point. You have all seen this. This is the famous X alpha hole. So there's this argument that actually it is a strange shape, but there is an error cancellation around, say, the central point, because if you have too deep a hole here, it's not deep enough there, and that kind of cancels, and you only are interested in the potential at the central point. But this hole seems very strange and very poor, but it's not so bad if you think about molecules. So here I have the exchange hole in H2 at equilibrium distance. At long distance it becomes very poor. We all know this. It becomes very extended. Half is on the other nucleus, and so actually this nucleus is screened by half an electron that remains here in the Hartree-Fock picture. This is why actually the Hartree-Fock density is not good. I mean, people always say that Hartree-Fock is pretty good for density, not for the two particle density matrix. But also Hartree-Fock densities are pretty poor. They are too diffuse because the nuclei are screened too much by other electrons that remain. You have to build the Coulomb hole, and then you get, say, complete hole of a depth of 1 electron. Now, if you look at the square hole, you see there's one thing that it does properly. It is local, right? And that is it's very good for many molecular properties, because this very bad mistake that Hartree-Fock is making does not occur here. So when you stretch a bond, the Hartree-Fock correlation error increases. So this is why always these total energy curves in Hartree-Fock, they are too narrow. So you have a too short bond length and a too high frequency. But if you have a hole that actually is local, it moves also when the nuclei are taken apart, then you get a much more even treatment of the properties around equilibrium. Now let me see, so this is something that is very well known. Hartree-Fock is actually, you can see the numbers, it's a terrible say method for bond energies. You see glaring errors. The typical errors are 50%, often more. LDA, we know, actually is not underbinding, but it is overbinding, and also not so good. When you look at X alpha, so I want to kind of stress this, X alpha is not so bad actually. It is better than LDA. Right. Often you get even the total energy, not so long, but of course it is not even. So here we have made a lot of progress with, say, the GGA approaches, but X alpha was not totally bad. I'm a little bit defensive here because people now make it look like you were silly to do X alpha calculations in the 70s and the 80s. It is dark ages before the light of the GGAs had been seen. But actually the X alpha method was rather accurate. So let me look at the next slide. Yeah, here are equilibrium distances and frequencies. And you can see actually that the equilibrium distances are in general very good. We did not have the feeling that, I mean, here should be much improved. So if you wanted to say geometries in general, also the frequencies, you can see, I mean, this doesn't get anything better with LDA. Actually, it's a bit, let me go back. If you do LDA, you can see here that like the total energies, the bond energies, get worse. And And we thought at the time that we understood why, because LDA is just X alpha has exchange only LDA, that is X alpha, plus correlation from the electron gas. But then of course people say, yeah, but correlation in molecules is totally different from correlation in an electron gas. So why would you expect that things improve when you take the correlation energy from the electron gas? Things get worse. Right? The electron gas, and this I still feel, is not a good model for the correlation in molecules. In molecules, everything is determined by the nuclear frame. Yeah, just recently I stumbled on this paper by Lövdin. Since we are here in Sweden, I should mention this. One of the foundational papers in theoretical chemistry is Lövdin's paper where he introduced the natural orbitals. But something that people forget is that at that time there was no contempt for the X alpha method. Lövdin discusses this very seriously, and he proposes actually that Slater's exchange hole approximation, and it is, as we have seen, it is actually an exchange correlation approximation. We could say exchange hole, but Slater already since '53 would call this an exchange correlation approximation, rightly so, I think. And Lövdin said, yeah, maybe this is the best local approximation to the non-local potential that featured in his equations for the natural orbitals. It's actually not true. I mean, these local potentials create rather different orbitals from natural orbitals for, say, for the virtual part, the weakly occupied ones. Okay. Yeah, I already mentioned this X alpha and LDA, DDA. They work for molecules in general better because they use localized holes. Now, this is a demonstration of what I mentioned. If you look at Hartree-Fock, you can see that the energy curve, it is too narrow, so you get your equilibrium distance is too short, your frequency is too high, and that is already better with LDA. And then we have, of course, the GGAs, and many people will talk about this, which also make the energy much better. But the point I want to make, and that's for the rest, is that actual holes are determined by the nuclear frame. They are, in that respect, an electron gas approximation is not physical. Okay, one can write the Hartree-Fock exchange term as rho integrated against the potential of the exchange hole. And then there's an old theory, Luken pointed this out. You can write the exchange hole as minus the square of a whole amplitude if you write this whole amplitude as a sum over the occupied orbitals, where the coefficients of the occupied orbitals depend on the position R1. There is, in a sense, there is a kind of correlation, of course, built into exchange. We call this the jumping Fermi hole, because if you are in a region of the system where the square root of the density is, so I suppose you localize the orbitals, then where the square root of the density is about equal to a local orbital, only that orbital will contribute to the whole. So if you move through the shells of an atom, you see that a whole shape jumps from one shell to another one. Now, this is a picture of exchange holes where you can see at different positions of the reference electron, and you can see that also this exchange hole is completely determined by the nuclear frame. Here is an example. If your reference position is inside the 1s shell, the hole also has completely the 1s shape. So we went to density matrix functional theory because I think it offers the perspective of much more accurate hole modeling. So an answer was that we said, okay, if you take the complete exchange correlation hole, we also try to write it as the square of a whole amplitude. And we express this whole amplitude as a linear combination now of all the natural orbitals, also the weakly occupied ones, with coefficients that depend on the reference position. And if you do this, then one ansatz is that you can say, and you can see the analogy with the exchange hole, the coefficient is determined by the natural orbital and its occupation number over the square root of the density. And then you can, I will not go into this in detail, go to all kinds of arguments why this would be a very good approximation for the total exchange correlation hole. You need permutation symmetry in the 2-electron density matrix. It should properly integrate, should be self-interaction free. And our answer, it becomes exact when you have high Z 2-electron atoms, and that's what I want to show. It also, let me see, yeah. It also handles the molecular dissociation correctly. So this is the total energy expression that you end up with, and you can see that it's actually a small modification of the Hartree-Fock energy expression. It only introduces now the natural orbital occupation numbers, but you see that what was the exchange part is now the exchange correlation part, only needs the exchange integrals. Actually, Müller in 1984, so prior to us, actually derived also the same expression, but that came from an atomic physics consideration. And I will stress, say, the molecular context. It was later modified by Göding and Omrigar, and Sanya and Arias actually derived the same expression and called it corrected Hartree. If you look at how this works out for a dissociating molecule, you can see that H2 at long distance, there are only two natural orbitals occupied, the sigma G and the sigma U. They have both occupation numbers 1. And now you can see that if you take this expression for the whole amplitude, then when you fill in, if you have a sigma G with occupation number 1, let me see, let's take a reference position around nucleus B. Then you will find that the coefficient for the sigma G orbital will be plus over 1 square root 2. The coefficient for the sigma U will be minus over square root 2. And then if you combine the two, then you can see that the whole amplitude, when you combine this one with that one, becomes the 1s on B. So you actually build exactly the right whole. It should be minus the 1s electron on B squared. Let me see, does it move? I lost my touch. Yeah. So it becomes exactly this will be the right hole, and it comes from this ansatz for the exchange correlation hole. These are some pictures of now the Coulomb correlation hole. We subtract out the exchange part, and then you can see that we compare to a CI calculation, and then this, say, trial hole, it's very close to the complete CI hole. But the point that I want to make is it is completely determined by the nuclei in the system. And in my next slide, that is for the correlation hole in the helium atom for different positions of the reference electron. You can see that when the reference position of this CI hole, actually very close to the hole that we are using, you can see that the shape of this hole is again completely determined by the nuclear position. It's natural, of course. Atoms have shells and all these things. That's all determined by the nucleus. Here you see at this particular point, you get a completely polarization shape of the hole, but here you have a very different shape. And that you cannot, I still feel, you cannot get with any actually, say, electron gas idea, because this structure of that atoms and molecules have is absent there. Did it work out? Well, not at first trial. This is the square root n functional for the H2 molecule, and you can see that actually it is too much binding, and then you can analyze why this is. This is basically the assumption that we made that the exchange correlation hole is totally negative. That is not quite right, and you can see then if you develop this, some of the terms have the wrong sign. Particular terms, for instance, that have two virtual or weakly occupied natural orbitals in them, you have to reverse the sign. So with some what we call physically motivated adaptations, you can see this the C3 improvements. Then you can see that actually you can get this dissociation quite accurately. Now, what will prevail in the future? Well, will it be the physical approach? I call this the physical approach of increasingly better modeling of exchange correlation holes. Well, maybe. I say I hope so. I like it. But the criticism is, of course, it's again too expensive because you need all these integrals, which is a pity, and it makes it too expensive. Maybe I should show the next slide. I was a bit pessimistic when I made this last slide, but then I came across two recent papers where actually the whole, say, technical computational part of this method is much improved. In these papers, they show that I think they got codes that are 2 to 3 orders of magnitude faster than the existing open source program for this type of calculation. So you never can tell. I mean, it looks a little bit like ab initio development where also, of course, the technique of doing these calculations improves all the time. Yeah, then maybe the future is for the development of new and consistently more accurate functionals using only the density, the occupied orbitals and gradients of the density. I call this the DFT dream. John Purdue learned us to dream, but I would say Jacob had, it was a dream, John. It was a dream. Yeah. Maybe, well, we can also think about machine learning. I think if I look at the development of density functionals with ever more intricate forms, more terms, more constants, then I think there is maybe some future for machine learning algorithms that can do the best out of such developments. Maybe it's the future. But now I get older and I think I come back a little bit to the old quantum mechanical methods. I'm impressed by actually the improvements. There are ever more sophisticated correlation methods based on configuration interaction schemes. Like the coupled cluster idea was, of course, brilliant. And has brought us a lot. So in the very long run, now I'm talking about decades, it may be that actually this method with GPUs and then whatever is going to win. But I think it will need a lot of computer power. And that has come of methods like, I never thought about doing density fitting for basis function pairs because you get so many data and so much work. And now it is a method that is actually thriving. It improves method, and that is due to compute power. we could not do that in the 70s. Okay, this is my last slide. I think I'm well in time. Yeah, okay, thank you.
Thank you very much for this excellent introductory talk. So we have time for discussions or comments, questions, please. Paula.
Yes, so one of the big advantages of DFT is, of course, that it converges very fast with the basis set. much faster than in the initial method. So if now you turn to 1R DMFT, you are back to the whole electron repulsion integrals and so on. So how is the convergence with the basis?
I think we have not systematically investigated, but it must be similar to, say, the CI methods. Because I cannot see why that actually. So maybe you would, the way actually we approximated this exchange correlation hole. Maybe there are smarter ways, but the way we do it, I think you have the same basis set problem as ab initio methods.
Yeah, so like I don't call it the basis set problem. I call it a changing problem, because when you increase the basis set, you get more orbitals. So if you fix the active space, then everything converges exponentially. So the question, I guess, becomes whether these reduced density matrix theories, like how they converge with respect to the active space.
That's a good point, actually, because one problem of these methods is, say, the very weakly occupied natural orbitals, but they are not really necessary. So it's a very good opportunity to have smaller active spaces, and then I agree that, say, this whole basis set development problem becomes better. Yeah, that's a good point.
Can I ask you, when you start with the X-alpha approach and end up with something that looks like DFT, you have picked one of two possible routes. You know, the other route that I would ask you to compare with is, suppose you started out with Thomas Fermi theory, a true density functional theory already conceived of in 1927. Then you fast forward to Hohenberg-Kohn in 1964, when it was proved that that type of theory should in principle work, not in the form of Thomas Fermi, because it was already known not to work for chemistry at all.
Yeah.
But then, of course, you go one more year and you go to Kohn-Sham DFT, when they back off the density only, and you know, Kohn-Sham DFT, and you go on to modern DFT. But your approach, I mean, you really start from Hartree-Fock, don't you? You start from Hartree-Fock theory, and then you look at that and you say that, well, you know, that exchange part of Hartree-Fock, it's really like a correlation, but it's granted to you without the Coulomb effect accounted for. So then you say, all right, but we could model that that exchange part in the X-alpha manner, and then that hole that we put in, it could contain as well the Coulomb part. So there are really like two different ways of arriving at rather similar end results.
I would say we are not so hooked, at least up to this Hartree-Fock. I mean, I say X-alpha is an exchange correlation method.
Yeah.
Slater wrote this paper in 51 about this square hole, and people seem to forget that in 53 he wrote a paper where he actually introduced what we now say was the potential of the exchange correlation hole. He proposed actually to do CI calculations iteratively with this full exchange correlation hole. So then, and then his approximation he considered as this X-alpha approximation as an exchange correlation approximation. And this is what I showed for the H2 molecule, that it actually acts as a full exchange correlation approximation. And I don't make a connection with Thomas Fermi. I always thought Thomas Fermi was so bad for molecules that it didn't seem to me like a good starting point anyway. So I don't connect with Thomas Fermi. No.
So, as you mentioned, Evert, the X-alpha method of Slater comes from the early 1950s. Can you explain why it took 20 years to get it implemented? And
No. We should ask Slater. but actually, I think you know better. It was used in solid state physics all that time. As far as I'm aware, the band structure calculations were all done with a 10⁻³ approximation. I remember I was in touch at that time with the group of Don Ellis and Art Freeman at Northwestern, and there was, say, no hatred or contempt for, say, X alpha or ρ⁻². It was a complete different atmosphere from the ab initio quantum chemistry. And also, I have always the feeling that in the United States, people were more mild against X alpha. In Europe, there was really hatred. No, I missed your question. Yeah, why started Slater only in the late 60s to promote this as a molecular method? That I cannot tell you. I think he was a solid state physicist as far as I can tell. So he concentrated on band structure calculations. And he just realized at some point, or maybe Keith Johnson, that you could actually build a molecular code with similar methods as a solid state methods. But you needed this muffin tinning, and I don't know why it took so long before he started to do that.
Okay. The slow acceptance of DFT by the chemical community is not so strange. It followed exactly the accuracy. I mean, before 1990, the accuracy wasn't good enough to be useful.
I disagree.
Yeah,
I disagree. I hope to show this with this example.
There are some cases that work, some don't. That's not very useful.
No.
X alpha made a linear water molecule, for example, and so people stopped using it.
Yeah, but that was a bug in the implementation. So that's what poisoned the well.
Still, there are...
No, it's good that you bring this up, because I think, so we actually did a lot of work in the 80s in transition metal chemistry. And I would say that still stands. I mean, I'm aware that heat of atomization, there's a problem, but actually, like you know, chemists are not so hooked up on heats of atomization. You want to look at changes. What happens when you change some substituent somewhere? What happens when you introduce an relativistic effect? You get changes, and already those X alpha calculations actually reproduce those changes in general quite well. It's only
the energies are the point of interest.
Well, but how often do you need like this heat of atomization energy?
Atomization.
Yeah, so say the bond energy.
Yeah, you use it all the time. I mean, you have to break bonds and you form bonds and whatever, and it doesn't work, then it's not useful. And actually, it's not even useful without Hartree-Fock exchange still.
Okay, I think we'll stop the discussion there. Thanks a lot for your presentation and for the comments. And then we go on to the next.